So in this question, we're looking to determine a range of values for which a function is strictly decreasing. So we're looking at the behaviour of functions at certain points within it. Now, in order to do this, we have to realise some properties of the functions. Now, this here is a cubic. So if we were to sketch a generic cubic, it would look something like that. Or it would look something like that, depending on the sign in front of the x cubed. Now, because this x cubed is positive, it's going to be the first one there. Now, what we have to realise is that between certain sections, the function's always going to be increasing or the function's always going to be decreasing. And it's going to change at the turning points. These 2 points here. Now, before this, the function's always going up, so it's always strictly increasing. Between the two of them, the function's going down, so it's always strictly decreasing. Above here, the function's always going up, so it's strictly increasing. Now, this question wants us to determine the range of values for which it's strictly decreasing, so this middle set of values here. Now, what we're able to do is we're able to do this in a couple of different ways. The first set of steps are always the same. We have to determine these turning points. If we can determine these turning points, we've then got our values to work with, and then we can prove whether it's decreasing. And there's 2 techniques we can use for that, which I'm going to show you here. Now, firstly, we want to find the turning points. Now, point to note here is we only need the x values of the turning points. We're only worried about it as it goes along. When is it decreasing? We're not worried about the rate of decrease or how much it decreases by or anything like that. In this question, we just want where is it decreasing. So we focus on the x values. So to do that, firstly, we take the derivative. So in this case, if I find f dashed of x, I get 6x squared plus 18x minus 24. Now what I want is where that is strictly decreasing. So where it's less than 0. So what I'm actually going to do is I'm going to first find out where those turning points are. So what I'm going to say is I'm going to take that function and I'm going to factorise it. So I'm going to do a common factor first and get 6x squared plus 3x minus 4. And I'm then going to say that's 6 bracket x plus 4 x minus 1. So what I know is that on this diagram, negative 4 and 1, my 2 turning points exist. So I know that at those points, it's going to change sign. Now I can look at the graph and logically say to myself, well, between those it's going to be strictly decreasing. But we have to prove it. Now there's 2 different ways that we can prove it. The first way that we can prove it is by looking at the graph of the derivative. Now if you imagine we take the derivative and we sketch it, we know it's going to be a quadratic. It's x squared. We know it's going to be a quadratic. We know it's going to have roots when I've got x is equal to negative 4 and when I've got x is equal to 1. Now if I then sketch it, my quadratic is going to do something like that. So what that then means is here, between negative 4 and 1, my derivative is always negative. So I have a negative rate of change, i.e. a negative acceleration or speed, so it's going to strictly decay. So I can say, therefore, it's decaying. So I've shown it graphically. Another way I could show it is by using a nature table. So you could imagine I've got my nature table here. Now normally we'd use this for turning points and calculating the nature of the turning points. Same idea here as well. So I've set up my nature table with my 2 turning points here. So I've got negative 4 and I've got 1. I've got my line for my derivative f dashed of x. And I've got what the graph looks like and my value for x. So I'm going to look at just below negative 4. I'm going to look at just above negative 4. I'm going to look at just below 1. And I'm going to look at just above 1. So I know at negative 4 and 1, the derivative is going to be 0, so it's flat. If I look at any value below negative 4, size of the number is going to be bigger than 4, the sign is going to be negative. So if I add 4 onto it, I'm going to get a negative answer. If I take away 1, that's always going to be negative as well. So I'm going to get a negative times a negative, which will give me a positive value. That means that my graph is coming up. If I then look at any value above negative 4, but below 1, because that's the interval that we're in there, let's say negative 3, for example, or 0, what I'm going to get is I'm going to get a positive bracket and a negative bracket. Positive times a negative will give me a negative. So it's decreasing. And that's similar behavior to just below 1. I'm going to get negative behavior again, because any value there in that range is always going to make the x plus 4 bracket positive and the x minus 1 bracket negative. So that's going to be going down as well. If I then look at any value above 1, the x plus 4 is always going to be positive at that point. And then the x minus 1, because the size of the number is bigger than 1, take the 1 away from it, it's always going to be a positive. So I'm going to have a positive times a positive. So I'm going to have a positive value, so it's going up. So what I can then say is this section here shows where it's decreasing. So I've proven it using a table of values. Now the last thing I have to do is state it appropriately. So what I can then say is fine, so it's decreasing. So what's the condition I want? It's decreasing. And that's when negative 4 is less than x is less than 1. Now you notice I've put strictly less than and strictly more than. The reason being, it doesn't include it. If I include negative 4, I have values of 0. So it's not decreasing at those values, it's actually stopped. We can't include the one in the negative 4, so don't make it less than or equal to or bigger than or equal to. It's got to be strictly less than, strictly bigger than. So please bear that in mind as well when you're writing down your range of values. So there you go, decreasing in that range there. So question like this one here, worth 4 marks. First mark, derivative. What am I going to do? Second mark is for determining where it's going to change. So you're negative 4 and 1, determining what's happening. Now the third and the fourth mark are linked. The third mark is available when you prove it. So either graphically, the method on the left, or using a nature table on the right, that's where mark 3 comes into play. Whichever one of those two techniques you use, it's got to be a valid technique. And then your fourth mark comes into play when you state it after proving it. You can't just state it and expect somebody to take it with a pinch of salt. They're not going to take it with a pinch of salt. They're going to say, well, you've not proven it to me. Why is it decreasing? It's that everlasting question. If you try and explain something to somebody like this, saying, oh, it's decreasing between negative 4 and 1, and they can turn around to you and say, why? You haven't proven it to them enough. You have to go back and state to them, well, it's decreasing here because graph of the derivative shows me this, or the nature table shows me this, or any other valid technique. So for example, you might even want to use the second derivative. But you have to still be able to show it. All right? That's the key thing to remember. So something like this is actually relatively straightforward. It's actually more the interpretive side of it that you have to remember. What does it mean by decreasing? So for example, derivative negative. How do we show it's decreasing? What does that mean graphically for the original curve, so the original cubic as I've shown up there? We have to bring all of these skills into it and bring all of these and bear them in mind. And if we can, we'll be able to nail a question like this, avoid that why question, and nail all 4 marks, easy peasy lemon squeezy.